Good evening, everyone from Sydney. Thank you for joining this workshop. So happy to see so many good friends, following this workshop. I will try really to be brief and try really to describe you what the recent development on, let's say, urban heat mitigation and also urban overheating. Urban overheating is the more serious, let's say, and the more documented phenomenon of climatic change. According to a latest, let's say, publication, there are about 13,000 overheated cities. And since the 80s, the number of overheating hours, in the world has almost tripled. There are more than 1.7 billion people which they live under very severe overheating conditions. At the same time, the problem of higher temperatures in our cities is not just a problem, of increase of the temperature in the very dense or in the central part of the cities. It is also, combined with an increase of the duration of hot spells. And you see, for example, between, let's say, the end of the previous century up to our days, that the number of, let's say, the hours or the duration of hot spells above 37 or 40 degrees has increased really tremendously. But unfortunately, it's not just that. The frequency and also the magnitude of heat waves has also increased very much. And you can see, for example, the number of heat wave, let's say, episodes with temperature above 37 degrees, how much really has increased during the very last years. So urban overheating and local climatic change is a phenomenon which is extremely well documented, and it has to do with the increase of the temperature in our cities. It has to do with the increase of the duration of hot spells, and at the same time, it has to do with the increase of the frequency and the magnitude of heat waves. Is there an interaction between global climatic change and local climatic change? Yes. Recent research has shown that during, let's say, heat waves, the local climatic change and the magnitude of urban heat island is increasing, let's say, tremendously. For example, in Sydney, during heat waves, the magnitude of urban heat island is increasing by 4 or 5 degrees. Which is the impact of urban overheating? First, there is a tremendous impact on energy. There is a very important impact regarding, the supply of energy and also regarding, let's say, the demand of energy. As it concerns the supply of energy, urban overheating is increasing, of course, the peak electricity demand, obliging utility to build additional power plants, which increase the cost of the electricity, creating important, let's say, problems of blackouts. It created important problems of, let's say, losses during the network, and also creating problems, regarding the efficiency of the power plants. As it concerns, the demand, it is obvious that higher temperatures increase the cooling demand of our cities and of our, let's say, buildings, and at the same time create serious problem, to the low-income population and so on. Do we have important data and do we know the real, let's say, magnitude of the impact of the overheating on energy consumption? Yes, we have very important data, and we know how much in general and in average or in every city is the penalty that we are paying because of the higher temperatures. And this brings us to the major problem that will, let's say, follow in the future or we have to face in the future. According to the existing, let's say, models, by 2050, we expect a tremendous increase of the cooling energy demand. And this, increase may be between, let's say, 1,000% according, let's say, to the models compared to the actual, let's say, energy consumption for cooling, or up to 2,200, let's say, % increase. Just to understand that according, let's say, to the statistics, the energy consumption for cooling of one Indian city, Mumbai, will be higher than the total energy consumption for cooling of the whole United States. And of course, you can understand that this will have a tremendous impact on, let's say, the price of electricity, the type of the fuels we are using, the emissions, the pollution, and so on. But apart, of the problem of the energy problem and the energy impact of urban overheating, higher temperatures have a very serious problem, and creates a very serious environmental problem in our cities. It increases tremendously the concentration of ozone. The concentration of ozone may exceed 300 units, while, the threshold is close to 110 units, and this is a very serious problem. According to the forecast, we expect a tremendous increase of the ozone because of the overheating in, let's say, the future years. And because ozone is a killer, this, let's say, it is associated with let's say, an important and very serious increase of, let's say, the heat-related or pollution-related mortality. At the same time, during, let's say, higher temperatures, the efficiency of, let's say, the power plant is decreasing considerably, and also the emission, of harmful pollutants like CO2, SO2, NOx is increasing by about 3.5% per degree. For example, during a day, during a heat wave, the emissions, of harmful pollutants by power plants, thermal power plants, is increasing, let's say, up to, if we have an increase of the temperature by 10 degrees, let's say, up to 30 to 35%, which is really a tremendous increase. Unfortunately, it's not only the environmental and it's not only the energy impact. Higher temperatures have a very serious impact on, let's say, the life and the quality of life of low-income population. We know very well that low-income population is living in non-proper housing, and they cannot really afford to pay for air conditioning. And for example, only in Europe, there are about 100 million, low-income population that they cannot afford really to use air conditioning, and they live under very high temperatures during the summer period. And this brings us to the major issue, the problem of health, how really higher temperatures affect really the health of the population. This is not, let's say, a deterministic association between higher temperatures and heat-related mortality and morbidity. Depends very much on demographic issues, socioeconomic issues, the health infrastructure. In average now, after so many years, and for the developed countries, because we don't have data for the developing countries, we know that the population which is living in the warmest neighborhood in cities have almost 6% higher risk of mortality compared to those that they are living in cooler urban districts. And this is the result of hundreds of studies, let's say, and data around the world in developed countries. How we can really face the problem of urban overheating? During the last 15-20 years, there is, let's say, a tremendous progress on the development of heat mitigation technologies. These mitigation technologies has to do with the development of materials, the development of greenery solutions, the development of, let's say, water-based solutions, and many other, solutions that we cannot all mitigation systems that we don't have the time to go through. But I like really to emphasize on the development of, let's say, cool materials and super cool materials during the very last years. And my colleagues later, they will develop the whole issue. We started 15-20 years ago with the development of the infrared reflecting materials, which are used now, let's say, almost everywhere in the world, that really may have, let's say, they may present up to 10 degrees lower surface temperature than the conventional materials, as you can see there. These materials are used either for passive applications in the outdoor environment or to create heat exchangers for ventilation purposes in order to pre-cool the air, in the urban environment. During the very last years, the development of new advanced thermochromic materials that they change the color as a function of temperature, has offered some tremendous, let's say, potential. Studies and experimental results have shown that the use of materials that they can be reflective during the summer or absorbing during the winter without really the intervention of anyone may present up to 21 degrees lower surface temperature than the conventional material. So you understand that these materials, when are used, for example, for ventilation purposes, in a passive or in an active way, may have a tremendous impact on, let's say, the cooling load of the buildings. We expect that in the near future, the development of the thermochromic materials, and especially the photonic thermochromic materials, may present, let's say, a much higher potential for cooling. However, what really is very important and where is the revolution on material science, it has to do with the so-called photonic materials. Materials that present a very high reflectance to solar radiation, 96, 97%, but at the same time, they present a very high emittance in the atmospheric window, let's say 8 to 13 micrometers. So the total, let's say, emitted energy may, let's say, or radiation may escape to, let's say, to the space. These materials, which are developed during the very last years, present subambient temperatures, and I like to show you the results that we have last summer, for example, in the Australian desert, where we have let's say, developed and tested this material. And you can see, for example, that under the sun, 1,000, let's say, watt per square meter, temperature about above 30 degrees, 40 degrees. These materials presented about, let's say, 5 to 10 degrees sub-ambient temperature. So these are natural air conditioners without to use even 1 kilowatt hour, for cooling purposes. We, let's say, tested these materials in a big mitigation project we have in Riyadh, in Saudi Arabia. And according to all the calculations we have, we are able to decrease the temperature of the cities up to 4 or 5 degrees during the peak. Of course, these materials may present a problem during the winter period because, let's say, may create some supercooling. So we have developed modulation techniques which change the emissivity and the reflectance during the winter. So you may have a material that is absorbing during the winter period, and this can be used for ventilation or in a passive way, and can be, let's say, reflective during the summer period to offer percooling. So these materials, when are used, in the built environment, may offer preheating and percooling, or even heating and cooling, actually, during both the summer and, let's say, the winter period. We tested this material in Calcutta, and we have seen that it is possible to decrease, let's say, the peak temperature of the city up to 4 degrees during summer and increase the temperature during the winter by, let's say, 2 degrees. On the other hand, a new technology that has to do with fluorescent materials that my colleagues will explain later present a very high potential because these materials do not absorb, like the conventional materials. They emit immediately a very high part of the radiation which is, let's say, received. In this case, we have tested these materials, and you will hear about this later, and we have, let's say, succeeded to decrease the surface temperature of this material up to 30 degrees, so 15 to 20 degrees. So this is a very high, these materials present a very high potential for passive or active, use for cooling and percooling. Actually, we're developing fluorescent and photonic materials together, which really present a very lower reflectance, so it can be used, let's say, in pavements everywhere, color materials, and at the same time present sub-ambient temperature. So where we are, while 15 years ago, we were able to decrease, let's say, the temperature of our cities up to 0.5 degrees and decrease the surface temperature of our materials in a passive or active way up to 4 or 5 degrees. The development of the new materials may, let's say, decrease the ambient temperature up to 2 or 3 degrees, but at the same time decrease, let's say, the surface temperature of the materials up to 20 degrees, which is a tremendous potential for cooling and let's say, percooling. So I like to conclude by saying that the development of these mitigation technologies offer a tremendous potential really to face the problem of cooling, and also at the same time help during the winter period. Improve, thermal comfort in our cities, improve health, improve the economy, offers an important, let's say, mitigation, offers important energy, let's say, benefits, improve the environmental quality, and so on. Just to tell you that the use of these materials, and Ricardo will explain later, when are used in, let's say, in Sydney, in the roof of our buildings, may decrease the cooling demand of, let's say, the city up to 49%. At the same time, may decrease tremendously the peak electricity demand and also decrease the consumption of energy. As it concerns the low-income population, these materials may decrease, the peak temperature of, let's say, these houses up to 10 degrees during, let's say, the summer period. Also, data coming from more than 60 cities around the world, mainly from the United States, shown that the use of these materials may really decrease tremendously heat-related mortality and morbidity. So, in reality, we know very well, actually, that the actual energy consumption for heating, and these are results from Sydney, the red dots present, the cooling demand of a conventional, let's say, house. The yellow one presents the heating demand. This is what is happening today. If nothing happens by 2050 because of the global and regional climatic change, the cooling demand will increase by a factor of 3 without having an important decrease of the heating demand. The use, let's say, of mitigation technologies may decrease the cooling demand up to 30 or 40%, which is very important. However, when we combine, these materials and the other mitigation technologies in an active way, so we are using as an adaptation policy, in this case, we may have the potential to decrease up to 80% the cooling demand of the buildings and up to 50 or 60% the heating demand of the building. So in reality, there is hope with the development, of these new materials all around, let's say, the world. So I like to conclude and let's say just inform you that actually we have this very serious problem of urban overheating. Thousands of cities present, very high temperatures. Billion of people lives under, let's say, very high, temperatures during the day and during the night. This increases the cooling energy demand up to 100% in specific places, increase the peak electricity demand up to 10%, increase heat-related mortality up to 40%. These are the bad news. The good news are that we are able now to decrease, let's say, the temperature of our cities, and there are more than 250 large-scale, let's say, implementations all around the world, up to 2.5 or 3 degrees. We expect in the near future will decrease the temperature up to 4 degrees or 5 degrees, decrease the energy consumption of, let's say, for heating purposes, for cooling purposes, up to 50 or 60%. At the same time, decrease heat-related mortality by, let's say, 30 or 40%, and also the peak electricity demand up to 20%. Thank you.